Okay, in the last class we discussed about nuclear fission process. Okay, so some of the basics of nuclear fission process that we just discussed in the last class. Now we will discuss about a little more about fission process, especially the fission of uranium nucleus, and then we will go to the fission reactors, and after that we will go to fusion reactions. Okay. So today we will be discussing about fission of uranium. In the last class we discussed about the basics of nuclear fission process, and we discussed about the spontaneous nuclear fission reactions where you do not have that potential barrier or that activation energy is not required. So that graph with that activation energy just that we just discussed in the last class. Just draw here. Okay, so here in the last class we discussed with this curve for that energy of nucleus, and versus that deformation parameter R. Okay, so that was something which will start from here and will go just like this. And the maximum, then it will come to some 1/r fashion. Something like this. So in the last class, we discussed about this curve. The energy of the nucleus against that deformation parameter R. So this is the ground state energy of nucleus. Okay. So that nucleus require this much of energy, more energy, this much more energy required, and this energy is that potential barrier, okay, or we call it as activation energy. So the nucleus require this much of energy to have that nuclear fission process to break that paranuclei into two different nuclei. So in this region, if the nucleus is having this much of energy, that maximum energy, or more than that, that of that activation energy, then the nucleus will start split around this region. Okay. So this is almost that point, at that point when that nucleus is having this much of energy, more than that activation energy. Okay. If the nucleus is at this point, the energy of nucleus is at this point, then it is over that activation energy. Then that nucleus can undergo nuclear fission process. Otherwise, if the nucleus is having this much of energy, that ground state nucleus is having this much of energy, then it will not readily go to nuclear fission process. And there are some nucleus which does not have this activation energy. Also, they will spontaneously decay, and they will not be having any of that activation energy or the potential barrier, so that they will be having only this curve. Okay, so from the ground state it will decay. So they spontaneously decay. Otherwise, we have to give some energy to make it excited to this level. Okay, then it will overcome that activation energy or potential barrier, and that will decay through this nuclear fission process. So that we discussed in the last class. Now we will discuss something about fission of uranium, where you do not have that uh, this much of energy, so it requires some energy in some form, and it will go to that nuclear fission reaction. Okay, so let's consider as an example, we can have different particles which can interact with those nucleus which is in the ground state, and then that nucleus can go to the excited state, and if that excited state energy is larger than the activation energy, then that nucleus can become then can fission into different doctor nuclei. So one of such method is that the neutron induced fission process. Neutron induced fission process. So in this case, we use neutrons as our particles. Okay, so here we consider very low energy neutron. In this particular case, we consider low energy neutron like thermal neutrons. Okay, normally we can use high energy or low energy. In this particular example, we use low energy neutrons. So the low energy neutrons, in other words, we can say thermal neutrons. These are having very low energies in electron-volts. So these low energy neutrons are bombarded with uranium nucleus. Then the uranium nucleus absorbs these neutrons. Okay, and that uranium nucleus will go to the excited state, and which will be larger than that activation energy, then go to that fission process. So the reaction will be like you have a neutron which is absorbed by an uranium 235. Okay, so uranium 235 and will go to the excited state. When it absorbs that uranium, it will become uranium 236, and which will be in the excited state. And from that excited state, it will go to the ground state through fission process, and it will give you the product nuclei or the daughter nuclei plus some nu n. Nu is a constant here. Okay, some a new number of neutrons. So this is constant. This nu is constant. Okay, so it will give you the products as x and y plus some number of neutrons. So this is the basic reaction, the fission process, which is going to happen to this uranium 235, which is absorbed by this thermal neutron, low energy neutron. So when this uranium 235 absorb this neutron, thermal neutrons, it will go to the excited state. Okay, and it will become uranium 236 because one more neutron has absorbed, and the total number of nucleons increase. That will increase the mass number by 1, and it will be in excited state. So in ground state, this uranium 236 will not decay. Okay, it will not undergo that fission reaction. But when it is in excited state, it will go to that decay because this excited state will be more than that activation energy. So in this particular case, if you want to calculate what is the Q value of this reaction, so the Q value will be equal to the energy of the parent nuclei plus that neutron. So that will be, let's say, the mn, that is the neutron mass, plus the mass of uranium 235. So I should write the mass of uranium 235. Okay, so this much times c square minus m into uranium, so the mass of 236 nucleus, okay, times c square. So if you calculate this difference, mass of neutron plus mass of uranium 235 into c square, that is the energy of this product, sorry, the parent nuclei plus that neutron. Okay, and then you have this excited nucleus of this uranium 236. So what is that mass of uranium 236 in the excited state? That has to be multiplied with c square. That you will get energy of that nucleus. If you take that difference, then you will get that Q value. What is the energy which is liberated in that process? So this is found. You can also take this part. Okay, so it will be like mass of neutron plus mass of uranium 35 into c square minus mass of all these things. Okay, mass of this x product y daughter, and then we have this number of neutrons here. So you take mass of all those things and multiply with this c square and take the difference between these two. That also will give you that energy which is released in this nuclear fission process. That is nothing but your Q value. Okay, so that Q value is found to be somewhere 6.6 mega electron volt. So if we calculate by substituting those values, and now if you want to know what is that activation energy, so the activation energy for this particular uranium 236 nuclei, so the activation energy of uranium 236, that is found to be somewhere around 6.2 mega electron volt. This is an average value. This may be 5.8 to 6.2. Different models will give you. So 6.2 mega electron volt of activation energy, and 6.6 is that excited state energy level. Okay, so when you compare these two, when you have that uranium 236 in that ground state, it will not be having this much of energy. But when it is in the excited state, then it will get this much of energy, more energy, 6.6 mega electron volt energy for that excited state nucleus. So and the activation energy is 6.2 only for that uranium 236. So what we are talking about is that when it was in the excited state, so sorry, when it was in the ground state, it was having some E0 energy, let's say, and when it went to that uranium 236 in that excited state, so that will be having E0 plus 6.6 mega electron volt of energy. Okay, and the activation energy here, if you calculate the activation energy somewhere here, that is the maximum energy or potential barrier that you have. So this energy is somewhere 6.2 mega electron volt. Okay, so which means that I mean this difference, this is nothing but that difference I'm saying. So this difference is 6.2 6.2 mega electron volt. So this activation energy. Okay. For this uranium 236. So in the ground state it is E0. So in from the ground state, if the uranium 236 want to go through that nuclear fission process, then it needs 6.2 mega electron volt, additional 6.2 mega electron volt to overcome this potential barrier, this activation energy or barrier, potential barrier, okay, which is having energy of 6.2 mega electron volt. So from the ground state, uranium 236 will not go through that fission. Fission will not happen because of this barrier, this activation energy, this much of activation energy required. But when it goes to the excited state by absorbing that neutron, then it will be in the excited state with energy, more energy of that 6.6 mega electron volt additional energy, and this 6.6 mega electron volt is more than this activation energy 6.2 mega electron volt. So in that case, nuclear fission will be uh, possible. Okay. So when that uranium is in this uranium 236 in the excited state, it will undergo through that nuclear fission process by this reaction. It will produce two daughter nuclei and some number of neutrons. So this is what will happen when you have these low energy neutrons which are absorbed by uranium 236. That will give you uranium 236 in the excited state, and further that will decay. That will produce that daughter nuclei X and Y plus some neutrons. Okay, so this is possible. So by this method, by using that neutrons, bombardment of that neutrons, okay, we can have this kind of nuclear fission that is possible. So when there is a nucleus which is having ground state energy, which is smaller, and it requires more energy to cross that potential barrier. So then you have to give some external agent, external energy through some particles. So here we use that neutrons, low energy neutrons, then we excite or those nucleon or nucleus, and it will overcome that activation energy or potential barrier and splits into two different nuclei plus few number of neutrons. Okay. So that's about the uranium 236 decay, and by this way we can have this nuclear fission process. So this is neutron induced nuclear fission process. Now if we consider another example, let's take a neutron which is absorbed by this uranium 238, and it will become uranium 239 in the excited state. And the Q value of this reaction is around 4.8 mega electron volt. Okay, and the activation energy of this particular nucleus, that is uranium 239 in this case. So this is nothing but around 6.2 mega electron volt. Okay, so here you see Q value is 4.8 mega electron volt, which means that the energy of this excited state from that ground state, that is 4.8 mega electron volt. So from ground state it is having this much of energy for uranium 239. So it is in the excited state with energy 4.8 mega electron volt more from that ground state energy level. Okay, but it is activation energy 6.2 mega electron volt. So this energy is not enough to cross this activation energy 6.2 mega electron volt. So this uranium 239 in the excited state will not undergo fission reaction. Okay. So the nucleus, if you consider nucleus which is absorbing these neutrons, okay, and which are going undergoing those fission process, okay. So in that case, in such nuclei, if you consider, the potential barrier will not be there. So after absorption, the nucleus will go to the excited state. So when they go to the excited state, then they are having enough energy, which is more than that activation energy required. So no more potential barrier is there. So they then from there, the nucleus readily go to that fission process, because potential barrier is not there, activation energy is not required, and the nucleus is already in that excited energy state. So such nuclei are called as fissile nuclei. Okay, such nuclei are called as fissile nuclei. Just check this I, E or Fi, fissile nuclei. So these nuclei will not be having those potential barrier. Okay. So this nuclei, so if you consider that nuclear fission that we just discussed, okay, when they are having the excited nucleus is having more energy than the activation energy, which causes the nuclear fission readily, as there is no barrier formation in such nuclei. So such materials in which very low energy neutrons, very low energy neutrons can get absorbed and fission without any potential barrier formation. Such nuclei are called as fissile nuclei. Another example for this type of nuclei is that you can say uranium 235 that we just discussed here, 235 absorbing that neutron. Okay, you can also have this is 230, I think it is 238. There are some examples for this fissile nuclei. Uranium 233 also you should check. So there are different nuclei which is having these properties, where you just so these nuclei just absorb those um, neutron, and will be having more energy than that activation energy, and readily go through that nuclear fission process without potential barrier, any kind of hindrance. Okay, so such nuclei are called as fissile nuclei, and in this case you can see this Q value is less than, this Q is less than that activation energy. Okay, so here the fission is not possible, fission will not occur. So in this kind of reactions where you do not have that much of energy, that Q value which is not that much of the activation energy, then you have to give some kinetic energy to this neutron. Suppose if you are accelerating these neutrons with some more energy, and that accelerated neutron or neutron with high energy, which is going and hitting with this uranium 238 nuclei, okay, and it is get absorbed. So total energy will be different now, because the neutron already has have some energy which is kinetic energy, which is more as we compared to the thermal neutrons. So when it is accelerated and these neutrons are having enough kinetic energy, and that neutrons are approaching to this uranium 238, so in that particular case, this uranium 239 in the excited state will be having more energy. Okay, when that neutrons which are having more kinetic energy, or we call it as energetic neutrons. Okay, we call in the just before that reaction, we just call them as thermal neutrons. when the neutron has very low energy. Okay, but when the neutrons are very highly accelerated and they are having more energy, okay, and that energetic neutrons are coming and hitting to this uranium 238 nuclei, and that is absorbed. So when they are absorbed, that this uranium will become 239, and that will be in the excited state plus some energy because of that energy of that neutrons. Okay. And in such cases, this nuclear reaction also feasible, which means that if you are having high energy neutrons, which is bombarding with this uranium 238, and which will give you that uranium 238 in excited state, that can lead to uh, nuclear fission process when that Q value, which is large. So in that case, your neutron will be having more energy. So high energy neutrons, then that Q value is more and the activation is overcome. Activation energy is less than that of Q value. Then that is also possible. We can have nuclear fission in that. Okay. Now, if you look for that fragments, that uranium, which is after fission process, what will be the fragments or daughter nuclei which are resulting. So there are different types of products for any nuclei, uranium nuclei you consider. So for example, uranium 236 you take. So this can be, this can undergo for that nuclear fission process, and it will produce xenon plus zirconium plus 2 neutrons. So this xenon is 140 and 54, and zirconium, which is 94 and 638. Okay, and again this can again go through some other different reactions. So it is barium plus krypton, and we can see this is 139, this is 56 atomic number. Here we have 94 and 36, and this will be accompanied with 3 neutrons. And then we have cesium plus rubidium plus 2n, and this cesium will be having 141 as mass number and 55 as atomic number. Rubidium has 93 and 37. Then again it can go in some other way also, which is iodine plus yttrium plus 2n. This will be erpium, right? Just check that. 137, 53. Here you will be having 97, then 39. So these are the different series by which this uranium 236 can decay through that nuclear fission process. Okay, so that will produce, that can produce xenon, zircon, and then barium, krypton, cesium, rubidium. Any of these configurations that can be resulted from uranium 236 fission process. Okay. So when you consider this yield of these reactions, that yield of this reaction, if you consider, I will just put that axis. So if you consider this yield of this reaction, then so if you consider this is your x-axis, this is the y-axis. So here in the x-axis you have this atomic number, and the y-axis you have that yield in percentage. Okay, which means that how many number of neutrons that you will get. So nuclei. Okay, nuclei, that is daughter nuclei I'm talking about. So this daughter nuclei, if you consider how many numbers you will get. So when you consider that curve, then it will be almost like this. Somewhat it will be go like this, and then it will reduce to minimum. Then again it will increase. In this side it will be having a little more, but almost similar to this curve. So then it will go again. Okay. So it will be like this. So from this curve, we can see here we have that a by 2 value. You just draw it like that. So this is your a by 2. This is your mass number in the x-axis. So this is that a by 2. So in this particular case, I will write it in that exact number here. So here we have this maximum. This maxima is corresponds to I will draw it in a different color so that not get confused. So this maxima, this is coming around atomic number 95. So the scale you just make it in that scale. So this is coming around 140. Okay, so this is that a by 2 value, which will be around in this case you have a equal to 236. So this is your mass number. So a by 2 will be around 118. Okay, so this is your 118. So from this you can see that the a by 2 fractions are very small, which means that you look at here. So you have mass number 94 here, 94 here, 93 here, then you have 97. Okay, so from that you can see around that 95 it is getting more number of nuclei, doctor nuclei, and you can see here 140 here, 139, 141, 137. So around that 140 it is coming maximum. Okay, so maximum number of doctor nuclei with the mass number 140, around 140 is maximum, and also around 94, 95 it is maximum number of doctor nuclei that you will get. Okay, so 90 mass number with the 94, that the doctor nuclei with the mass number 94 is having some maxima, and 94, 95 is having some maxima, and mass number doctor nuclei with mass number around 140 is also maximum. Okay, and if you consider any nuclear fission with mass number which is a by 2, which means that the doctor nuclei are exactly splitting into half. Okay, that means the parent nuclei which is exactly splitting into half. Okay, so the doctor nuclei will be having similar mass. That means around 118. So this uranium 236 is splitting into same mass numbered nuclei with 118. So plus 118 will come. Okay. So this is very rare case. Or anywhere, for example, if you can also get somewhere 130. In this case, you can also get a 117 plus 117 plus 2 neutrons, because you have 2 neutrons which is coming out. So this is also a similar nucleon, sorry, similar nuclei, doctor nuclei. The same nuclei with half of that, around that half of the parent nuclei mass number. And this is what we have given this value. Okay, so there that probability or yield in percentage is smaller as compared to these 2 points. So from that we can see that the asymmetric fission is more probable as compared to the symmetric fission. So asymmetric fission are more probable than symmetric fission. Okay, so asymmetric fissions are more probable. Asymmetric fission means that the mass number of the daughter nuclei will be different. It will not be exactly half of that nuclei. So the mass number of one daughter nuclei will be larger and the other daughter nuclei will be smaller. Here you can see that here we have 140 and 94. So one is higher mass number, one is smaller mass number. You will not get the mass number which are almost equal. Such cases are less probable. We'll get, but as compared to this asymmetric fission process, this is having less probable. These are less probable. So getting doctor nuclei with similar mass number is less probable as compared to those of doctor nuclei with the different mass numbers. Okay, so those nuclear fissions are called as asymmetric fission, with the daughter nuclei having very different mass number. Those are asymmetric fission, and these asymmetric fissions are more probable as compared to that of probable symmetric fission. Okay, so that is what we get from this term. So now the question is that how much energy is liberated in this kind of nuclear fission processes. That we have to find out, and we will discuss something about that important point. So if you consider any nuclear fission process, let's say that X nuclei, S nucleus, which is going to Y and Z. So this is having mass number A, this is having mass number A1, this is having mass number A2. Okay, so the binding energy of A, if you consider that binding energy per nucleon curve that we already discussed. So I will just discuss that now. So let's put here. So here we'll be having this. Take this one. Now, if you consider that binding energy per nucleon curve that we already discussed earlier, so that will look like almost will be coming like this, and after this there is some small. So on an average, we can write it. You can plot it like this. Okay. So you have somewhere here, you have that A value. I don't think this will work. So let's take some A value here. Actually, it will come in that end. So let's take this A, that is the parent nuclei. Okay, and that will become doctor nuclei when that will convert into that doctor nuclei through fission process, and that parent nuclei split into that those nuclei with doctor nuclei with some small mass number. So they will come around this region that we already discussed in the nuclear fission process. So let's say some nuclei which one particular nucleus after fission which is coming in this range. So this is having a mass number around A by 2 plus A. Then let's say we have another daughter nucleus which is in A by 2 minus A, and in between these two we have that A by 2. So this is the point which is A by 2, and let's take that energies. So I should have drawn it a little more with some gap, but anyway. So this is the energy correspond to this, and let's take this as okay. This I will take this as the first one. So this is correspond to that. And I will take this as E1. Okay. So this point is nothing but E1 plus some delta, and this is somewhere E1 minus delta. Okay. So here I should have some more energy here. Okay. I should go like this, something like this. So this point is more having more binding energy per nucleon per binding energy per nucleon will be more here than here we have. So this point which is smaller. So this is E1 minus delta. This is E1, and this is E1 plus delta energy. Okay. And here we have A by 2 in this middle. So this A is converted into A by 2 plus A and A by 2 minus A mass numbers of those nuclei. That's daughter nuclei. Okay, so with mass number A by 2 minus A by 2 plus A, if it is symmetric fission, they will be having mass number A by 2 almost. Okay, so if they are asymmetric fission, then there will be A by 2 A plus A by 2 plus A and A by 2 minus A as the mass numbers of the daughter nuclei. Okay, I hope this is clear. And we have one more energy which is coming here. So that will be the energy of your parent nuclei is 0. Binding energy per nucleon for your parent nuclei. This is nothing but binding energy per nucleon in this axis. Okay. So this is the E0 is the binding energy per nucleon for your parent nuclei. E1 is that binding energy per nucleon for that A by 2 nuclei. And if you consider that asymmetric fission, there will be shift in that from that A by 2 value from plus A by 2 plus A and A by 2 minus A as the mass number of those daughter nuclei. And if you consider that, then you have from that symmetric fission that nuclei with A by 2 of mass number. From that, the energy will be shifted like E1 plus delta and E1 minus delta. Okay. So considering that, so the binding energy of parent nuclei, binding energy of the parent nuclei, let's take A, binding energy of A, and that will be nothing but E0 times A. And binding energy of daughter nuclei, I will take first daughter nuclei, that is E1, so that will be A by 2, I will take first minus A, that will be E1, so I am talking about this one, A by 2 minus A, binding energy of this one. So A by 2 minus A, it will come E1 plus delta. Okay. So this is the binding energy per nucleon. E1 plus delta is the binding energy per nucleon. That is what we are drawing here. So E1 is nothing but binding energy per nucleon. So this has to be multiplied with that mass number, then only you'll get binding energy. Okay, binding energy per nucleon is E1 plus delta here. You can see from here. And that has to be multiplied with that mass number, then only you'll get binding energy. So that mass number is nothing but by 2 minus A. Similarly, Be2 for second daughter nucleus, it will be A by 2 plus A, and that will be given by E1 minus delta into A by 2 plus A. So these are the binding energy of the fragments or doctor nuclei. So if you consider these two, that the binding energy of the fragments, so that will be given by, I will just write here, binding energy of fragments, that will be nothing but E1. The first one is E1 plus delta, into A by 2 minus A, plus second one is E1 minus delta times A by 2 plus A. So this is the total energy, binding energy of those fragments or the doctor nuclei. So if you further reduce this, this will come as you can see E1 into A by 2. Just expand this, E1 into A by 2 minus E1A. Then we have plus A by 2 delta, then minus A delta, plus E1A by 2, then E1A by 2, E1A. So this is plus E1A. Then we have A by 2 minus A by 2 delta, then minus A delta. So some of the term will be getting cancelled, and finally you will get the result as E1A, E1, E1A minus 2A delta. So this is what you will get finally. Now you have that binding energy of A, which is the parent nuclei, which is nothing but that E0 times A that we already written above. Okay, so now what is the difference between these energies? So difference in binding energy for parent and daughter nuclei. So if you calculate this, that will give as delta of binding energy. Delta of binding energy will be nothing but that E0A is for parent nuclei. Okay, so E1A is for daughter nuclei. E1A minus 2A delta for daughter nuclei binding energy, minus parent nuclei which is having E0A. So this will give you A you take common, so E1 minus E0 into A minus 2A delta. So this is the change in binding energy from that parent when it after fission, when it becomes those neutron nuclei. Then there will be some change in binding energy, that is this. Okay, so the binding energy when you consider that parent which is reduced by, when you consider okay, I will explain that. So if the fission process is symmetric, or you can just say that if it is a symmetric fission process, So this implies delta in binding energy. Delta in binding energy will be, what is that? Symmetric means your A, look at this figure. If it is symmetric, then this A should be 0. If it is symmetric means both the doctor nuclei will be having A by 2 as your mass number, exactly almost half of that parent nuclei, that is A by 2. So if it has to be symmetric, then your this A should be equal to 0 for symmetric fission. Then only that A by 2 will come for both daughter nuclei. Okay. So for symmetric fission, symmetric means your A equal to 0, which implies this E1 minus E0 times A, capital A. Okay. For asymmetric fission, you will be having those values. So I'll say for asymmetric fission, that is A will not be equal to 0. In such cases, delta in binding energy, that will be same as the above expression. So E1 minus E0 times A minus 2A delta, because your A is not 0 now. So considering these two equations for symmetric and symmetric case, for symmetric fission, you have E1 minus E0 times A. For asymmetric fission, we have E1 minus E0 A minus 2A delta. Okay. So for symmetric fission, you will get more energy released. Here we have less energy released, because the binding energy difference from that parent to daughter nuclei is less here, and binding energy difference for in between that parent nuclei and daughter nuclei is more here, because here you have E1 minus E0A minus 2A delta. So whatever energy you are getting here, that has been again reduced by 2A delta value. Okay, so that energy release will be smaller. But when you consider here, it is directly E1 minus E0 times A. There is nothing to subtract. So this is more, okay, as compared to this. So binding energy difference between that parent and the daughter nuclei will be higher in this case for the symmetric fission, and which is smaller in this case. Okay, so which means that in this case, when that parent nuclei is here, we just show as like this. So and the daughter nuclei is here. So this energy gap is more. This energy gap is more for that symmetric fission. If you consider that for asymmetric fission, that will be your parent energy level will be here somewhere, that binding energy I'm saying. So then your daughter nuclei plus that that will be something like this. So this gap between daughter nuclei and parent nuclei uh, for symmetric fission, this will be larger, and for asymmetric fission, this will be smaller. So this much of energy will be released. EP minus E T. This much of energy is released in this particular case. I'm just representing it in that energy state form, but the exact reaction relation is this. So that much of energy will be released. In this case, EP minus ED will be released, same energy, but that gap is different. So here the energy will be smaller because your ED is more here as compared to this case. Here your ED, that doctor nuclear energy level is much more lower state. Okay. So this case you will get more energy. This case you will get less energy for asymmetric fission. So here we have the energy level of daughter nuclei, which is very small, and the difference from that parent daughter nuclei will be larger. And in this case, we have that the daughter nuclei's energy level is higher. Okay, and the difference between parent and daughter nuclei will be small. So in this case, we get more energy. Here we get higher, lower energy. But when you consider these energy levels, here we have low energy level for daughter nuclei. Here we have a higher energy level for daughter nuclei. So this should be more probable. Okay, this should be more probable because your daughter nuclei, that nuclei which are formed after fission reaction is in the lower energy state as compared to this particular reaction. They are in the higher state. In this case, ED is much more higher. EP is fixed, parent energy level is fixed, and when it is asymmetric fission, this daughter nuclear energy level is higher as compared to that daughter nuclear energy level for the symmetric fission. Okay, so in that case, if you consider for that daughter nuclei which are having lower energy levels, this should be more probable because always the system tries to minimize it. We were discussing about these two neutrons. So these two neutrons which are called as prompt neutrons because these neutrons are coming out along with this fission process. So simultaneously these neutrons also forms. So that's why it is called as prompt neutrons. It will happen along with that fission reaction. Okay. So from why these two neutrons are coming out, for that we have to consider that neutron proton ratio. So for I will just draw that to curve. Okay, this one and again. So if you consider that neutron proton curve that we already discussed discussed before for that decay processes. So this is your Z. Okay, x-axis is Z, and this one is neutrons. These are neutrons, and these are protons. So this curve will give you something like uh, some straight line initially. Then it will, when it goes higher, and then it will deviate from that. And if you consider this curve, you will be having stable nuclei around this line that we already discussed. So around this line we have that stable nuclei. We can say that stable beta nuclei, which will be around this line. So this is that n versus z curve. This we already discussed before. Okay. So when you consider this particular curve and your nuclei that is having more number of neutrons at this particular stage. So let's take that is around here. Okay, I'm talking about this uranium-236. So if you consider that uranium-236 or 235, those neutrons, so those nucleus, then those nucleus will be having high Z neutron to proton ratio. For example, if you consider, okay, here itself we can consider uranium-236 also. Let's consider uranium-235 case, uranium-235 with some 92 of atomic number. That will give you that n by z ratio. That is z is nothing but 92. Okay, so it is 92 to 235. From 235, how much it is? 140, 143. Right? So this ratio, you take n by z ratio, which is larger. N by z ratio is for uranium like nuclei, which will be very large, because when you go heavy nuclei, number of neutrons will be much larger than number of protons. Okay, so this ratio will be high. Okay, so this when this uranium, which is somewhere here at the end of that curve, with more number of neutrons as compared to protons, that will come to this around somewhere here after fission reaction. So they will be coming somewhere here, one daughter nucleus somewhere here, and another daughter nucleus somewhere here, right? So that nuclei will be coming after that fission reaction. So that ratio of proton to neutron, that will be same. After nuclear fission, process also. I'll just write it here. After fission, the ratio of NZ, I should not write it like this. The value I should write, okay? So the value of N by Z ratio, okay? This will be same. So this N by Z for daughter nuclei and parent nuclei will be same after fission. Okay, so those nuclei, those daughter nuclei, which is coming after fission process, will be somewhere here. First daughter nuclei and second daughter nuclei will be somewhere here in this straight line, which means that they will be having same n n by z ratio as of that parent nuclei. So in this straight line, if you take, that slope will be same for this straight line. So that n by z value for this daughter nuclei, these are the daughter nuclei. So for this daughter nuclei, the n by z value will be same, ratio will be same for both the daughter nuclei immediately after that fission process. Now these nuclei which are having n by z ratio which is higher, as you can see from here. So this ratio, okay, I will just calculate that how much it is coming so that it will be more easier to understand. So just calculate 143 to 92. Or I will just check for uranium 236. I don't know what is that. You just check that uranium 236 how much it is coming, or I will just explain, because you check how much that atomic number is coming. So then you can take that fraction for uranium 236. For uranium 235, it is coming like this. So this fraction is coming around 1.554. Okay, so this 1.55 will be same for that daughter nuclei also. Daughter nuclei, both the daughter nucleus, both. So for both of those nuclei, daughter nuclei will be having the same 1.55 fraction for n by z value. Okay, which does not mean that the number of neutrons and number of protons will not be same. They will split. Okay, but the ratio of number of neutrons to the proton, that will be 1.55 after fission. So you just check with that uranium 236 also with that atomic number. So this from that this nucleus will be coming to the same in the same this straight line, so that the slope of that n by z value will be same. N by z is the slope here, because we have in y-axis we have neutron, in the x-axis we have z. So n by z is nothing but the slope of this straight line, this line, any line which is forming in this particular graph. So that will give you n by z value. So this straight line, if you have a straight line from the origin to this point, that is your parent nuclei, and then if you draw that straight line, then n by z value will be same all over this straight line, because that slope will be constant. So this daughter nuclei will be having same n by z value immediately after that fission. So but for stability, this nuclei, daughter nuclei has to come to this point. Okay, for stability, from here also this point, it has to come to this point. So then only it will be in that stability line. Okay, so in order to make that stable daughter nuclei, when it comes to this point, it has to release some neutrons in that process, and that is coming here, 2 neutrons. Okay. This is one of the source from where that neutron is coming. So that immediately after fission, n by z ratio will be same for parent and daughter, but this daughter nuclei will not be in that stability line. Okay, so in that case, those daughter nuclei come to this stability line by emission of neutrons. That neutrons are these prompt neutrons. Okay, in order to reach in that stability line. That is what is happening. So these are the prompt neutrons, and if you consider that reaction time, fission reaction time, if you consider this will be around 10 raised to minus 15 to 16 range. Let's say 10 raised to minus 14 to 10 raised to minus 16 second. So within this much of second, fraction of seconds, that reaction will happen. This fission will happen. So within this much of time, that neutrons will come out along with that fission reaction within 10 to the power minus 40. So this is around the femtosecond range. That is 10 to minus 15 second. Okay, so that is the fission reaction time. So within that fraction of time, fraction of seconds, that neutrons also will come out along with that daughter nuclei. Now, this xenon which is formed will not be stable. Okay, let's say xenon 140 that is just formed after fission reaction 54, and this will again decay into cesium 140, and that is 55 through negative beta decay. You can see from here this mass number is constant 140, and the atomic number increased by 1, 54 to 55. That means that it is negative beta decay where you convert one neutron into proton. So the total number of nucleons will be same. One neutron is converted into one proton. So number of nucleons same. So mass number remains same, but number of proton increases because neutron is converted into proton. So 54 will change to 55 and it will form cesium. Again, this will again continuously go through beta decay, negative beta decay. Then it will form barium 56 140. So 140 will not change. Again, it will go through negative beta decay. Then it forms lanthanum with 57 and 140. Again, this is not stable. Again, go to negative beta decay, and that will form again 58 here, and we have 140. So this is stable. Okay, this one here it is stable. So this much of negative beta will happen. So in this beta decay, what is happening? One neutron which is converting to proton, and that neutrino, all those things will come along with this. Okay, so this is negative beta decay. Neutron which is coming converted into proton, and neutrino also will come along with this reaction. So that you had to consider. So this is neutrino, which also come out in this negative beta decay process. So this is proton. Okay, we will be having that proton plus an electron. So this will be an anti-neutrino because electron will come as anti-neutron. So this proton, which will be formed, and it will increase this atomic number from 54 to 55, 56, 57, and 58. So when it reaches 58 with this link, that will form the stable nuclei. Okay. Now this is continuously beta decay process. That negative beta decay process is continuously happening to this nuclei, and it will become stable. So in each cases, the excess number of neutrons are reduced. Okay, and then it will come to that stability line. So immediately two neutrons comes out along with that fission process. Okay, then after that those daughter nuclei again continuously go through these beta decays, and it will form this stable nucleus. This is cerium. Okay, that will form, and so in each case this one neutron is converting to proton in each step, so that excess number of neutrons are converted into proton, and then that will come to this stability line. See here, the stability line, that it will reach into that stability line. So initially the neutrons are immediately gone after that fission process. Then still it is not stable, it will be somewhere here, some in the intermediate position, and again it will release those excess neutrons in the form of negative beta decay, and it will increase number of protons and comes to that stability line. So after reaching in the cerium CE, that this particular nucleus, and then this particular nucleus, that is stable, it will become stable. Similarly, all other doctor nuclei, most of them will be in unstable form and immediately go through this negative beta decay and become stable. Okay, and another example I will give because it is having some importance. So another example I will give for this fission process. Take uranium-238, which is going through that this is erbium, I think. So this will be having some mass number of 94 and atomic number around 39. This plus iodine with 53 atomic number, and then mass number is around 137 plus 2 neutron. So this is another fission process where uranium-238 split into two daughter nuclei, which are erbium and iodine. Okay, plus 2 neutrons also released. So these 2 neutrons, these are prompt neutrons. I already told that prompt neutrons, which are forming immediately after that fission. And when you consider that iodine, there are two different reactions with it. For example, that erbium, which will undergo 94 and 39, which will go through that again negative beta decay, which will become zirconium. Okay, so this will form 97. Sorry, this is okay. I have made some. Then this will, you check this 94, 238 should come. So 2 neutrons here, 137 here, 137 plus 2 will come 139. Okay, so this should be 7. This should be here, you have to get 238, right? So 96 plus 137, that will not come. How much this will come on? 238. 238 should come as total. So this will be around 137, 130, 141, and 231 only. This 231 plus 2 neutrons. So 231, 232, 233. So I need 5 more. So just check that what is that iodine, which is, I think I have written somewhere above also. I will just check that. Iodine, how much it is coming? iodine, which is 137, I wrote here. Okay, that is right. So then, if I consider this as 97, so I need more neutrons then. Okay, just check that this is 97 I wrote here. I will just clarify that in the next class. Okay, that will go to the zirconium. So here 97 and mass number will not change. Then it will go again. You just check these numbers. Okay, so this is 97 uranium 238. So 97 plus 7, it will become 104 and 130. So 234 it will come. So you just check whether it is uranium 230. So this should be different. Okay, this should be 6. Okay. Uranium 236. That uranium 236, I think I have wrote this. So that will come. Okay, now it is right. I think I have written here. I don't know whether it is same or not. Just check. So yes, here it is uranium 236, right? Here it is uranium 236. Okay, so now this also uranium 236, not uranium 238. This is uranium 236, which is decaying into this erbium and iodine that we already written up also. And that will come like this. Then that is erbium, which is 97. That undergoes through this negative beta decay and zirconium forms. With this will increase. So this will become 40. And again go through negative beta decay. And it forms xenon with this one is sorry, this is neodymium. This will form neodymium. So this. So this will become 41 and 97 again. Then this will NB, and this will go again through that negative beta decay to molybdenum MO, and with 97 and 42. So all those excess neutrons, first it will relate to neutrons, that those are prompt neutrons. Then again there is excess of neutrons. Then again it will go through that negative beta decay, converting one neutron into proton in each step. It will reduce the number of neutrons, and it will increase it will also reduce that n by z ratio, and come to that stability line. Okay, so here it is stable in molybdenum. So this is stable. This also accompanied, for example, this zirconium, which will be in excited state. This niobium, this is also in excited state. So this also accompanied with gamma radiation. Okay, it is not only that the beta decay happens. These things also will give you gamma radiations, gamma rays out. So when we took that gamma decay process, we told that when negative, then when beta decay process happens, okay, when beta decay process happens, it also accompanied with that gamma decay, because when beta decay process happens, the nucleus will be de-excited to, sorry, it will be decayed into that excited state. From the excited state, it will go to the ground state through gamma decay that we discussed in the decay processes, beta decay processes. So when this decay process happens, this zirconium will be in the excited state, and it will go to the ground state by emitting gamma decay. And then it will go to that beta decay again because of excess of neutrons. And then it will become that neodymium, and that also will be in the excited state, and it comes to the ground state by emitting gamma radiation. So in all these processes, nuclear fission processes, this beta decay process of that daughter nuclei will be accompanied with this gamma decay also. Okay, so please keep it that in mind. So when you consider that iodine, iodine 137 with the 53, which also undergo through because it is also in it is not stable, so which also can undergo through that negative beta decay, and which will form xenon, and xenon with the mass number will be same, and the atomic number increased by 154, then something different will happen. So when after that this xenon, again this xenon with 136 and 54 will form, and plus 1 neutron will be released in this particular. So this is not a beta decay process. This is not beta decay process. This xenon will convert that mass number into 137 to 136 with a constant atomic number, which means that some isotope of xenon, the isotope of xenon. So this xenon convert into some other isotope of xenon that is with the same atomic number with a different mass number 136, and it will release 1 neutron in this reaction. So this is not a beta decay process. This is another that excited state to ground state. It will come. So this is stable. So when that excited state to the ground state, when it becomes from the unstable to the stable, when it is moved, it will release 1 neutron. Okay. This is also happening. So this particular neutron which is coming out, which is called as delayed neutrons. Delayed neutrons. So these are not coming from that immediate fission process. So those are prompt neutrons, and these are delayed neutrons which are not coming because of beta decay. Okay, which is also coming out just through this process. The isotope of xenon, which is converted to an isotope of 136 mass number from 137. Okay, so in this reaction, 1 neutron is released, and this neutron is called as delayed neutrons, which are not from that fission immediately after that fission. It is not from that. So it is not prompt neutrons. It is not through that beta decay also. So these are some different types of neutrons. These are called as delayed neutrons because this will happen in a few minutes. This will take some few minutes to happen to get that neutrons come out from that reaction. And in the prompt neutrons, this will happen, as I said, it in the at 10 raised to 14 to 10 raised to minus 16, minus 14 to minus 16 seconds. This will happen. These neutrons will come out, but this will come out after some minutes, 1 minute, so 2 minutes, a few minutes. So this is delayed neutrons. This will come out within 1 minute or 2 minutes, something like that. So these are the delayed neutrons which are also coming out from the decay of those daughter nuclei. This is not from that beta decay. This is not from that fission reaction. This is a different process, and these neutrons are called as delayed neutrons. Okay, so if you consider the fraction, okay, if you consider that fractions of this particular process, then we can say that it is around 0.02 per fission. I mean that number of delayed neutrons that will come out in the nuclear fission process will be around 0.02 per fission, which means that if you take 50 number of nuclear fission process, one delayed neutrons will be there. One delayed neutron will come out. Okay, 50 number of nuclear reaction, fission reaction. If you consider one neutron coming out from that, all those 50 number of nuclear fission reaction is from this. It will be that delayed neutron one. So 0.02 per fission. And if you consider the above one, that prompt neutron fraction, this one, and this will be around 2.45 per fission. So per fission, you will get 2.45 number of neutrons on an average per fission for the prompt neutrons. So each of the fission will produce 2.45 fraction of neutrons, which does not mean that it will be some fraction of neutrons, which is an average value. Okay, so in some cases it will be 2, some cases it will be 3. So if you take an average, it will be around 2.45 number of neutrons per fission. Okay, that is the fraction value. That what we are calculating is this number. So that is new that we represented initially. So that will be somewhat 2.45 per fission. Okay, so that's all about. Also, this gamma radiation that I just told, this gamma radiation also called as delayed gamma radiation. And if you consider here also, there will be gamma radiation with this reaction when that uranium, which is converting into this daughter nuclei plus 2 neutron, this is also accompanied with some gamma radiation, some energy in the form of photons, and these gamma radiations are called as prompt gamma radiations. Prompt gamma radiations. So we have all those configuration. We have prompt neutrons, delayed neutrons. We have prompt gamma rays and prompt that prompt gamma rays and delayed gamma rays both. Okay. So these are the basics of uranium 230 or uranium in general, uranium uh, fission processes. And when you have that excited state uranium, you can easily uh, exceed that activation energy. And such nuclei, we call that as fissile nuclei, all those things that we discussed. Then we discussed something about the energy of this nuclei which are formed. Then we found that the theoretically asymmetrical fission process will be less probable and symmetrical fission will be more probable. But in experimental, we can see that the symmetrical fission are less probable. And that is when we consider that the remaining part of that equation, that the neutrons which are also coming from that reaction, fission reaction, that is also contributing to this, because whole energy are not carried out by this uh, daughter nuclei. Some energies are also carried out by these two neutrons here, and some are carried out by these gamma radiations. Okay, and also that nuclear decay, sorry, beta decay also happened to this erbium and iodine, and that also having that proton, sorry, that neutrino particle which are coming out, the electron which are coming out, those also take this energy in this reaction. So all these particles will take that energy difference from that parent to daughter nuclei if you consider. So it is not the whole process. You have to consider the other particles also. And when you look into that, then the symmetric, from the experimental point of view, symmetrical um, symmetric fission are less probable as compared to the asymmetric fission. And now we'll discuss in the next class, we will discuss about the fission reaction and some continuation from here that we will continue from in the next class.